VLSos here. This is a video lesson for geometry on dilation. Dilation is a transformation. It's a geometric transformation we can do to shapes. A common term for it is size change. And dilation is related to the concept of similarity. If you have two shapes that are dilations of each other, then those shapes will be similar, with all that it means to be similar, with equal corresponding angles and proportional corresponding sides. If shapes are similar, then, and you can prove that they're similar, then all of the mathematics of dilations applies. So knowing one leads to the other. Here we have the geometry of a dilation that has started. We have a point and rays coming off those points that intersect with the vertices of a shape. We're prepared to use these rays, these lines, to help guide us to do a geometric dilation. This here is called the point of dilation. We use these rays as a guide. If we're going to change the size of this rectangle, and we could choose a specific way to change the size, like with a zoom factor or a scale factor of 3, which means that all side measures are going to triple. They're going to multiply by that scale factor. Then I could start with a side length like BC and find along these rays where the vertices, the corresponding vertices to B and C in the larger shape that I'm about to draw, will go on these lines. I need to find a distance that's going to be 6. If I start here and I draw a line so that it starts on this vertex, this ray where B is, and it ends on this ray where C is, then I've focused on changing the size of just that side. I changed it from a measure of 2 to a measure of 6, and I use the graph paper to help guide that. This side here, BA, starts as a measure of 1, and if it's going to change size by a factor of 3, it's going to become a side measure of 3, and be here along the rays, where A and the corresponding point are on the same ray, and B and its corresponding point are all on the same ray as well. The measure of this side is 3. I could do that to the other sides to complete the dilation of my rectangle. So dilation and similarity are related. These two are dilations of each other. We don't always need to grow. We can change the size of something by shrinking as well. They're dilations of each other. These shapes are similar. We could say that ABCD is similar to WXYZ because we created WXYZ by dilating ABCD. What does similarity mean? As a reminder, similarity, figures that are similar, mean that they have equal corresponding angles. This angle at D, if it's going to be a part of a rectangle, is 90 degrees. Its corresponding angle here, if we add the vertices that we talked about, WX, YZ, will be equal. Angle D corresponds to angle Z and are equal in measure. Similarity also means that they have proportional corresponding sides. Which means that we can set up a proportion, ratios that are equal to one another, with the side measures, and we'll do that. But let's also talk about the mathematics of dilation. Dilation always has a scale factor, the number that you multiply side lengths by to get new side lengths. We could also call that the zoom factor, just another term for the number that you multiply one side to get the next side length. And these can be thought of as a ratio of sides. But if you have two sides to compare in a ratio, you can do it in two ways. One comparison is going to be for growth, and one is for shrinking, changing size by getting bigger or smaller. Now, when we started out, we started with the smaller shape, and we created the larger shape. So that was growth or expansion. And the ratio of corresponding sides for this growth would be to compare the two to make a number greater than 1. The side length of 6 compared with the corresponding side length of 2 is a ratio that can be simplified to 3. Small sides got multiplied by 3 to create the size of the larger side. We could take the reciprocal of this for the shrinking ratio. We could reduce it to 1/3. In other words, if we started with the larger shape and we dilated by shrinking, then it's the same sides that we're using. We're just comparing it with a reciprocal. And this reciprocal is less than 1, so multiplying will shrink distances. You start with 6, take 1/3 of that, and you get the smaller side of 2. Proportional corresponding sides, when you have similar figures because they're dilations, is talking about these ratios. The corresponding side ratios are all going to be the same. They're going to be the scale factor, the zoom factor, the ratio of dilation. One more thing to say. We need to be careful, as always, when we work with diagrams. That justifying dilation or similarity when justifying dilation or similarity, it does not matter the way it looks. Don't trust your eyes. Just because two shapes look the same, maybe you have rays, maybe there's a point there, don't assume it's a dilation. What you have to go for is the math. The math must work. With how the diagram is labeled. If we started with this, and instead of one side measure of 6, which we know would make a correct dilation, if we saw all of this presentation, but instead of a side length of 6 here, let's say it was 7, which means that the ratio of corresponding sides would not be equal, it couldn't be a dilation. You wouldn't want to be fooled just looking at that and make an assumption that because it looks like something you would do when you dilated, that it is a dilation. You've got to set up the math. You've got to show the corresponding angles are equal, the corresponding sides are proportional to justify that it's a dilation. If you can't do that, you can't assume that it is.